Good morning everyone. My name is Sanvi Rastogi, roll number 205004, and my topic for the presentation is linear transformation. Let Vf and Wf be two vector space over the field F. Then a mapping T tells to from Vf to Wf is called a linear transformation when T of C alpha plus beta is equal to T alpha plus T beta, where alpha and beta belongs to V and C belongs to F, and T alpha and T beta belongs to W. If V equals to W, then T is a linear operator. The linear transformation T is also said to be a vector space homomorphism over field F or an F homomorphism. If it is 1-1, then it is known as monomorphism, and if it is onto, then it is known as epimorphism. So a vector space homomorphism over field F is known as isomorphism if it is both 1-1 and onto. For a linear transformation T tells to from V to W, the set of V is called the domain of T, and W in which the images of T are defined is called the codomain of T. The linear transformation that maps every element of V onto the zero element of W is called zero mapping. The set of all the linear transformations from Vf into Wf is the space L V, W. Range or image of T. Let T tells to from V to W be a linear transformation, then the image of T is defined as range of T is equals to image of T, which is equals to beta belongs to W, such that beta equals to T alpha, where alpha belongs to V. It is also denoted by IMT or RT. Null space. Let T tells to from V to W be a linear transformation where Vf and Wf are vector spaces. Then the set of all the vectors alpha of V such that T alpha is equals to 0 is known as null space of T. It is denoted by NT or kernel of T, that is KT. That is, NT is equals to alpha belongs to V such that T alpha is equals to 0. This is the condition for the null space when T alpha is equals to 0, where alpha belongs to V. Rank and nullity. The dimension of range T is known as rank of T, and the dimension of kernel of T is known as nullity of T. It is denoted by RT or PT and NT or VT respectively. There is a question. The following transformation for T tells to R square to alpha square is a linear transform for T x1, x2 equals to x2, x1. Given that T of x1, x2 is equals to x2, x1, we will let alpha as x1, x2 and beta will be y1, y2, where C belongs to R. Then T of C alpha plus beta is equals to T of x1, x2 plus y1, y2. Then T of C alpha x1, x2 plus y1, y2. Then T of x1, y1, cx2 plus y2. Then T is a linear transformation from R square to R square when T of C alpha plus beta equals to Ct alpha plus beta. There are some particular transformation. First is zero transformation. Let Vf and Wf be two vector space over the field F. Then a transformation T tells to from V to W is defined as zero transformation when T alpha is equals to theta, where alpha belongs to V and theta belongs to W. The condition for zero transformation is that zero transformation is also a linear transformation when let alpha, beta belongs to V, C belongs to field F. Then it can also be written as C alpha plus beta belongs to V. Then T of C alpha plus beta is theta, such that T of C alpha plus beta is equals to C theta plus theta. Then T of C alpha plus beta is Ct alpha plus T beta. Second is identity property operator. Let Vf is a vector space, then function I tells to V is defined as I alpha is equals to alpha for all alpha belongs to V. Identity operator is also a linear operator. Let alpha, beta belongs to V and IF equals to alpha and I beta equals to beta, where alpha belongs to C belongs to F and C alpha plus beta belongs to V. Then I of C alpha plus beta is equals to C alpha plus beta. Then I of C alpha plus beta is equals to C of I alpha and I beta. That is, identity operator is a linear operator. Then the third transformation is negative of a linear transformation. Let Vf and Wf be two vector space over the field F and T tells to from V to W is a linear transformation. Then we define a map that minus T tells to V to W is called a negative of linear transformation when minus of T alpha is equals to minus of T alpha. When alpha comma beta belongs to V and C belongs to F, then C alpha plus beta belongs to V. Then the transformation of C alpha plus beta is equals to minus of transformation of C alpha plus beta, which is equals to minus of Ct alpha plus T beta, since T is a linear transformation. Then minus of Ct alpha minus of T beta is equals to C minus T alpha and minus T beta. Then T of C alpha plus beta is equals to minus of C transformation of alpha plus transformation of B. So negative of linear transformation is a linear transformation, that is minus T is a linear transform. Let Vf and Wf be a two vector space and T be a linear transformation from V to W. Then first we will prove that T theta is equals to theta dash, where theta dash belongs to W. Second, T of minus alpha is equals to minus T alpha, where alpha belongs to V, and T of alpha minus beta is equals to T alpha minus T beta for all alpha comma beta belongs to V. First we will see that for all alpha belongs to V, then theta also belongs to V. Then alpha plus theta is equals to theta. Then transformation of alpha plus theta is equals to transformation of alpha, since alpha is linear transform. Then T of alpha plus T of theta is equals to T alpha. Then T alpha plus T theta can also be written as T alpha plus theta dash. Then from here we get that T theta is equals to theta dash. Second part, T of minus alpha is equals to T of taking minus outside, that is T of minus 1 alpha, then minus 1 of T alpha, where T is a linear transform, which comes out minus T alpha. Third, T of alpha minus beta is equals to T alpha plus minus 1 of beta. Then T alpha plus T of minus 1 beta, we will get that T beta alpha minus T beta. Thank you.